My name is Dave Strain. I'm president of APS. It's a systems development company focusing on improving the performance with respect to energy on HVAC systems. The particular part of the system we're looking at today in this video is called the mixed air. The mixed air is a combination of outdoor air blended with return air from the building, and it serves the purpose of providing air to replace the exhaust that has been exhausted by your fans from the building to keep the building slightly pressurized. It provides air to match the code requirements for air quality in the building, and also is used for cooling to cool the building. The issue we have with it is by design from the early 1900s was that the temperature was at a fixed temperature of about 13 degrees Celsius. This is a temperature that is cold enough to take care of you on the hottest day of the summer, and so as a consequence, it's too much cooling for all the rest of the year. That then would have to be added heat to compensate for the overcooling. This particular video is presented in 4 different slides. The first is one presenting the basic fan system to show you the relationship of the mixed air to the rest of the fan. This drawing illustrates a typical HVAC mixed air system. It is essential for everyone in our industry to understand how much energy can be wasted when mixed air is controlled illogically. Mixed air is a combination of return air from the building and fresh outdoor air. Air is drawn from the occupied space by the return fan. At that point, the control system has 2 options. It can exhaust the air outdoors through the exhaust dampers, or it can recirculate the air back toward the supply fan through the return air damper. When outdoor air is introduced, it blends with the return air to create what we call mixed air. The portion of the outdoor air in this mixture varies as outdoor air conditions change. Fresh outdoor air serves 2 primary purposes. First, it provides ventilation. Second, when outdoor air conditions are favorable, it can provide free cooling. Ventilation itself performs 3 important functions. It replaces the air removed by the exhaust system, helping maintain a slight positive pressure within the building. It assures compliance with minimum ventilation requirements established by building code. During cooler weather, it can provide free cooling and reduce the need for mechanical refrigeration. One of the most significant shortcomings in our industry is the way this mixed air is commonly controlled. In many systems, the mixed air temperature is maintained at a fixed set point, typically around 13 degrees Celsius. Air at 13 degrees Celsius almost always contains more outdoor air than is required for ventilation. As a result, the system operates as though it is continually in cooling mode, regardless of the actual needs of the occupied space. This creates a major energy waste. The mixed air introduces unnecessary cooling, while the heating system is forced to consume additional energy to offset that cooling that never should have been introduced in the first place. In many cases, this occurs even when none of the zones served by the HVAC system requires the cooling. A logical control strategy takes a different approach. It allows the zone with the greatest cooling demand to determine the amount of cooling required, and only after that zone has fully shut off its local heating device. The mixed air temperature is then allowed to reduce naturally to the least cool value that still maintains occupant comfort. This minimizes simultaneous heating and cooling and dramatically reduces energy consumption. At home, we instinctively apply common sense. We do not open windows in the winter and then turn up the furnace to compensate for the heat loss. The same principle should apply in commercial buildings. The HVAC system should introduce only the amount of cool outdoor air required for ventilation and legitimate cooling needs, not excessive cooling that must later be offset by heating. Applying this simple logic can significantly reduce energy waste while maintaining the same level of occupant comfort and reduce greenhouse gas emissions. The second slide is one showing the impact of excessive ventilation, excessive fresh air into the air, into the heat requirements for a building. This drawing compares the same room operating under 2 different HVAC control strategies, conventional control logic and energy conservation logic. Scenario A operates using conventional HVAC control methods developed in the early 1900s and still commonly used today. In this example, the mixed air temperature is maintained at a fixed 13 degrees Celsius and the minimum outdoor intake is set at 15%. The thermostat set point is 21 degrees Celsius, and the room temperature is a stable 21 degrees Celsius. The scenario B represents the same room operating under energy conservation control logic developed in the 1970s. The thermostat set point and room temperature are identical to those in scenario A. Both scenarios' occupant comfort and room conditions are the same. The thermostat settings are identical and the space temperature remains 21 degrees Celsius. However, scenario A requires 82.6% more heat to maintain those conditions than scenario B. Both rooms experience the same heat loss to outdoor, 50,000 BTUs per hour, and both receive the required ventilation to satisfy quote requirements. The difference is that scenario A introduces an additional 50,000 BTUs per hour of cooling through the supply air system because of the fixed 13 degrees Celsius mixed air temperature. That unnecessary cooling must be offset by additional heating energy to maintain the room temperature. In scenario B, the control logic allows the warmest zone in the building to determine the supply air temperature, subject to a minimum limit of 13 degrees Celsius. As a result, the system delivers warmer air whenever possible, reducing unnecessary cooling and corresponding heating required to compensate for it. The traditional control method effectively forces cooling into the building under many operational conditions. While this practice has historically been referred to as free cooling, it often increases overall energy consumption, operating costs, and greenhouse gas emissions when the added cooling must subsequently be reheated. As this example demonstrates, identical indoor comfort can be maintained while significantly reducing energy use through more effective control strategies. The third image is a graph showing the relationship of the performance of a conservation circuit relative to the original design from the 1930s. This graph compares traditional mixed air temperature control with a demand-based control strategy. In conventional HVAC design, the mixed air temperature is a fixed 13 degrees Celsius, regardless of the building's actual cooling requirements. A demand-based approach works differently by allowing the warmest zone of the building to determine how much cooling is needed. Once the heating in the warmest zone has been satisfied and shut off, the mixed air temperature is permitted to float naturally between 15 degrees Celsius and 20 degrees Celsius. The blue line represents the cooling demand from the warmest zone. As internal heat gains increase throughout the day, the cooling demand rises accordingly. During the night, when internal heat gains disappear and the building requires only heating, the mixed air temperature increases while the outdoor air fraction is reduced to a minimum ventilation requirement. The black line represents the mixed air temperature actually required to satisfy the building's cooling demand, while the red line shows the fixed 13 degrees Celsius temperature used in conventional design. By allowing actual demand to control the mixed air temperature, the system operates with approximately 5 Celsius degrees less cooling, significantly reducing the heating energy required to reheat overcooled air and eliminating a substantial source of unnecessary energy waste and greenhouse gas emissions. The fourth slide is one that has two graphs on it. The upper graph is one that shows the performance of the system that another company had done a conservation circuit on the system, and they had misjudged the arrangement between the controllers. The lower graph is the improvements we had made to it, showing it a 49.75% improvement on the energy performance on the system. This page presents two performance graphs. The upper graph shows the system operation after a major controls contractor completed an energy conservation retrofit. Despite the upgrade, the laboratory experienced significant occupant discomfort for nearly a year, and APS was asked to investigate to resolve the problem. APS agreed to correct the comfort issues at material cost only on the condition that the project could be used as a case study. That case study, Battle Against Climate Change, is available as an article on the APS website, apscontrols.org, and is also included in the APS Conservation Training Manual, beginning on page 8.63. APS redesigned the control sequence, resulting in the performance showing in the lower graph. The outcome was clear. All occupant comfort complaints were eliminated. The graph also demonstrated a substantial improvement in energy efficiency. The heat consumption was reduced by 49.75% over the conservation circuit installed the previous year by the large control company, when compared at the same outdoor temperature matched to within zero point 0.1 Celsius degree. This extremely narrow temperature range was intentionally selected to eliminate the influence of a varying outdoor condition and provide a precise apples-to-apples comparison of systems performance. Based on our experience, properly sequenced heating operation with mixed air control typically reduces annual heating energy consumption by approximately 20%, while also complementing other conservation strategies. On our website, apscontrols.org, there's an article titled Fighting Climate Worry. Within that article are links to two reports that are highly significant when considering the future of today's children. The first is a BBC report indicating that more than 50% of children are regularly worried about climate change. The second is a Stanford University report projecting that the world could exhaust its economically recoverable fossil fuel resources within the lifetime of the children living today. These findings underscore the importance of taking climate change challenges seriously and pursuing practical, effective solutions. Just as importantly, we need to demonstrate that meaningful action is being taken, helping to reduce the anxiety many young people feel about the future. With respect to controls logic and energy conservation, it is important to understand that no solution can be applied everywhere. What we are really teaching is comparable to teaching someone how to play chess. We can show you the moves and strategies that have been proven successful in addressing conservation challenges in the past, but we cannot predict every situation you will encounter in the future. For that reason, I encourage you not to simply memorize the concepts presented in the APS training manual. Instead, strive to understand them deeply. A thorough understanding transforms information into a practical tool that can be applied to new and unforeseen challenges. As Albert Einstein famously observed, information is not knowledge. Information alone has limited value. Knowledge is gained when information is understood and can be applied effectively in the real world. Thank you very much for your efforts with respect to climate change, and I believe that collectively, with everybody trying, we can make a major impact on the threat to the children's future.